Okay, so let us continue our discussion on analysis of spring mass systems. We had a non-autonomous system in front of us, but as we said that the solution is going to be incredibly long. So, we started off with taking a simpler case of the autonomous system and its solution using similarity transformation. So, let us continue our solution. The equation was m d2 x by dt squared plus k x is equal to 0. The equation was this, and the various relevant quantities that we developed in the previous lecture are like this. We have P, which is given as the augmented eigenvector matrix is root over m by k 1 minus I root over m by k 1. P inverse was 1 upon 2 times minus I root over k by m 1 I root over k by m 1 lambda was I root over minus I root over k by m 0 0 I root over k by m. Y dash was P inverse x. These are the quantities which we had from our previous lecture, and then the equation was y dy under bar by dt is equal to lambda times y under bar. We wrote the solution as y under bar is equal to e to the power lambda t times c under bar, where c is a constant, c under bar is a constant vector. So, following the method which we developed in the previous lectures, we can write e to the power lambda t as what? E to the power the first component here minus I root over k by m, the entire quantity multiplied by t, 0 0 e to the power the second element along the diagonal I root over k by m multiplied by t. Okay. I would refer you to previous lectures to convince yourself that this is what you will get. So, if this is the case, then what is the solution that we will get? So, I can write this as y under bar is equal to e to the power minus I root over k by m times t 0 0 e to the power I root over k by m times t multiplied by the constant vector c 1 c 2. Okay. So, now what I can do is I can write this back in terms of my original vector. So, my original vector was x. So, I can write x under bar as y as p multiplied by y under bar. Okay. So, therefore, what I will get here is this, that x under bar is equal to what is p P is I root over m by k minus I root over m by k 1 1 multiplied by e to the power minus I root over k by m whole multiplied by t 0 0 e to the power I root over k by m whole multiplied by t and the entire quantity multiplied by C 1 C 2. So, now this is the solution that you will get. How to proceed forward? So, what we can do is, so let me write down the last quantity again. Okay. So, the last quantity which you get is this x bar under bar is equal to p, and p is what? P is I root over m by k minus I root over m by k 1 1 multiplied by e to the power I t e to the power lambda t, e to the power lambda t was e to the power minus I root over k by m times t 0 0 e to the power I root over k by m t multiplied by C 1 C 2. This is your solution, but it is not very elegant. So, how would you get an elegant solution? Well, you will multiply these two quantities. This is a 2 by 2 matrix, this is a 2 by 2 matrix. So, your resultant matrix would be 2 by 2, and this is a 2 cross 1 matrix. So, your further resultant matrix would be 2 cross 1. So, you will get x and y, where x is the original quantity, y is dx by dt which you had defined originally. You will get the expressions for them. So, now you have a system where you write m d2 x by dt squared plus k x is equal to f 0 sin omega t, right. So, this is a non-autonomous system now, and what would be the solution procedure? It would remain, the steps would remain identical. Let me highlight the steps. I urge you to actually jot them down and proceed further with the trivial integration, multiplication steps and so on. So, I will write dx by dt is equal to y. So, here this would become m d y by dt plus k x is equal to f 0 sin omega t. So, I can write this as dx by dt is equal to 0 x plus 1 y plus 0 times whatever may the function of t be. Okay. And I can write the second equation as dy by dt is equal to minus k by m times x plus 0 times y plus f 0 sin omega t. Okay. So, from here I can write d by dt of x y is equal to 0 1 minus k by m 0 x y plus 0 f 0 sin omega t. Now, if you see this equation, what you will find is that the first two terms are identical to what we just now solved. The new term which comes is this one, which involves a function of time. So, a lot of the solution steps would remain identical, which means identifying the matrix A, and this matrix A in fact is the same matrix which we saw previously. So, therefore, the matrix A is the same matrix as the previous case, is the same matrix, and therefore, lambda 1 would be the same, lambda 2 would be the same, V 1 under bar would be the same, V 2 under bar would be the same. And since V 1 V 2 under bar are the same, P under bar would be the same, P under double under bar inverse would be the same, and so would be lambda. So, every step which we followed during the previous question, previous part would remain the same. The only difference which would come is here, that in this case now I can write this equation as, I can assign this as vector x. So, I can write here as d x under bar by dt is equal to, this is a x e x, which we did in the previous case as well, but I have a new vector here. So, let me call that vector as g under bar of t, right. So, again the first two parts were the same, you have the new g of t now. So, what is the solution procedure? D x under bar by dt is equal to a double under bar x single under bar plus g under bar. It is a function of t. So, let me diagonalize the matrix. I can write this as d by dt of p inverse x is equal to p inverse a p inverse x plus p inverse g t, right. So, I will put this also in bracket. Then what is going to happen? I will assign new variables. So, let p inverse double under bar x be equal to y under bar, and now I need to assign the vector which is a function of time as well, the input vector. So, I will call this as p inverse g under bar as b single under bar, sorry. Okay. So, if this be the case, my new equation would be d y single under bar by dt is equal to lambda y single under bar plus b single under bar, which can be rearranged as d y under bar by dt minus lambda y under bar is equal to b, and I will write an analogous equation as this d y by dt minus lambda y is equal to b. So, therefore, I know that the integrating factor would be in this case e to the power minus lambda t, which in this case would become e to the power minus lambda t. I know how to determine this. not very difficult. So, I will multiply this quantity on both the sides and solve for y. Now, when I solve for y, I will come across a situation where I would need b, because b is not known to me. Is it very difficult to know b? Well, not, because b single under bar is p inverse double under bar g, right, and what is this equal to? P inverse in our previous case was 1 over 2 multiplied by I root over k by m, I root over k by m 1 1. This was my P inverse, and I would multiply this by g, and g was nothing but 0 f 0 sin omega t, right. So, I can determine the vector b, and that vector b which I get would be used here. Again, you will have to be careful about the initial condition vector that you would get. Make sure that you post multiply it and not pre multiply it for the compatibility of operations, and then once you solve for y, by solving this you will get y, right, y under bar. What you need is x under bar, and therefore, x under bar would simply be p multiplied by x by y under bar, sorry. Y under bar. Okay. So, our original definition was y under bar is equal to p inverse x under bar, see here, right. So, therefore, x would be p times y, and then when you solve this equation, you will get the solution which would involve sines and cosines as well as functions of t which would influence your dynamics from the viewpoint of the influence of the external forcing function. Okay. So, I have a set of equations, and I have also found out their solutions. So, while I would encourage you to use pen and pencil to actually determine the solutions using the exact same procedure, what I will do today is I will write down the equations and their solutions, and then we will visualize their dynamical behavior. So, we will spend time on understanding the dynamics rather than the repetitive steps which we have hopefully already understood. So, the first equation that I have is this. D to x by dt squared plus x is equal to 0. Does it look familiar? Yes, in fact, this is an undamped free system, and the solution is x of t is equal to C1 cos t plus C2 sin t. Again, this is quite expected, we have already solved this particular problem. Let us see how does the dynamics look like. So, I have f of x is equal to C1 cos x plus C2 sin x. Quite expected. You see that there are oscillations which are sustained. Okay. The amplitudes do not change. So, the amplitude here is 1.414, 4.414, 1.414, 1.414 and so on. Okay. So, we saw that the equation is d x by d2 x by dt squared plus x is equal to 0, and the solution is quite simply x of t is equal to c1 cos t plus c2 sin t. Autonomous system, the behavior has been very well understood. Now, secondly, I have now d2 x by dt squared plus x is equal to sin of t now. Now, this is a non-autonomous system. I have a non-autonomous system, and if you solve this using similarity transformation, the answer that you should get is c1 cos t plus c2 sin t, well, the effect of the autonomous part, plus minus 1 by 2 t cos t, right. See, this is the effect of your forcing function. Let us see how does your solution look like. So, I will write here g of x is equal to c1 cos x plus c2 sin x minus 1 by 2 x cos x. Okay. Now, you see what happens here. The oscillations start with the same condition, they start at the same condition, you see here the initial condition was the same, and the magnitudes, the amplitudes of oscillations keep on increasing with time, they keep on increasing with time, right. And why is it happening so? Because see, this part in both the cases remains the same, but the effect of autonomous part is now augmented with the non-autonomous part, which you see here, and the effect is that the amplitudes of oscillations keep on increasing. What is the meaning of this? What is the physical significance? If there is a spring which is oscillating and there is no external force and there is no frictional force as well to damp it, it will continue the oscillation, right. But whenever it is reaching any particular location externally, if you are keeping on providing it with some magnitude of external force, then on top of this same oscillation and magnitude, the external force will increase the amplitude of oscillations, and therefore, this will keep on increasing with time, right. So, now we saw that not only does the autonomous part come into picture giving the system oscillations, the external force is increasing the oscillations in time. Further, let us see if we can look into further equations. Now, I have here two equations, d2x by dt squared plus dx by dt plus x is equal to 0. The solution is given as x of t is equal to c1 e to the power minus t by 2 sin root over 3 upon 2 t plus c2 e to the power minus t by 2 cos root over 3 by 2 t. Okay. So, what kind of equation is this? This is our autonomous equation with damping. And on top of this, now I do this d2x by dt squared plus dx by dt plus x is equal to sin t. Same forcing function as I used previously, and now what I get is x of t is same what you get for the autonomous part, c1 e to the power minus t by 2 sin root over 3 by 2 t plus c2 e to the power minus t by 2 cos root 3 by 2 t plus the effect of the external forcing function, and in this case it would be minus cos t. If you solve this, you will get this. Okay. So, let us plot both of these and compare the solutions. So, I have f of x is equal to c1 e to the power minus t by 2. So, minus 0.5 x times sine 0.5 times square root of 3 x plus a very similar quantity here but this would be cos. What do you get here? The system had oscillations, but the system was damped. Okay, this is a system with damping. So, therefore, the oscillations went to 0. Okay. Now, what you get here is something like this. So, I have same solution minus cos t, okay, minus cos t. And you see what happens here. You had initial transients, what you can see here, but then as time increases you simply have a very periodic behavior. And why is that happening? That is happening because you have the solution which involves this decaying factor, and the decaying factor is a function of time. So, as time tends to infinity, this particular exponential factor will have no significance, and then what you would be left with is simply the cosine term here, this term, and this is what you see here, sustained oscillations with the same amplitude. Okay. So, what you learn from here? So, let us summarize what we learned here. We had sustained oscillations, right, and on top of this sustained oscillations, when you put an external forcing function, then the amplitude of oscillations kept on increasing. This is t, this is x. Then you had damped oscillations, t x, and on top of the damped oscillations, when you put an external function, the oscillations maintained the amplitude. This means that what we can conclude is that every non-autonomous system can be fragmented into autonomous systems, the effect of autonomous part and the effect of forcing function. The forcing function would augment the effect of autonomous part. I encourage you to solve the equations which I gave you using different forcing functions. The equation that we solved that we analyzed today were of the form d 2 x by dt squared plus dx by dt plus x is equal to sine of t. Now, instead of sine of t, you can use cosine of t, you can use e to the power t, you can use e to the power minus t, or you can simply use a ramp function which is nothing but t. And in all the cases, you will see that as time t tends to infinity, the dominant behavior would come from the part which does not involve exponentials. If you have exponential which is negative in power, the exponential part will die down and the rest of the part will be your dominant solution. In contrast, if you have an exponential which has a positive power, then as time t tends to infinity, it is the exponential which will dominate your dynamics and the other part will become insignificant. So, we will stop here today and continue our discussion on higher order systems from next week onwards. Thank you.